Hi, in this video we are going to talk about AVL tree, which is a self-balancing binary search tree. So first thing, it is a binary search tree, which means all the values on the left are smaller and all the values on the right are greater. Second thing, it is height balance. How does it maintain the height balance? It has this rule that the difference between heights of left subtree and right subtree should not exceed 1. And we call this difference as balance factor. Balance factor is absolute difference between left height and right height. Let's see this example. This is an AVL tree. I've written the balance factor with every node here. Balance factor for this is 0 because there is nothing on the left, nothing on the right. Both the subtrees have height 0, zeros. For this node, the balance factor is 1 because the height of left subtree is 1 and height of right subtree is 0. For this node, balance factor is 0 because height of left subtree is 2 and height of right subtree is also 2. For this node, balance factor is 1 because height of left subtree is 1 and height of right subtree is 0. Let's see this tree. This is not an AVL tree because there is a node whose balance factor is 2, greater than 1. Balance factor of this node is 2 because height of left subtree is 2 and height of right subtree is 0. We are counting the height as number of nodes in a tree. So this side has height 2 and this side has height 0. So this is not an AVL tree. Let us now talk about AVL tree operations. Please note that AVL tree search, it's going to work same as BST search. So search is same. Insert and delete are the operations which are complex in AVL tree when compared to BST. Because these are the operations, they make sure that height remains balanced, that AVL tree property is followed. Whenever you do an insertion, it does some restructuring to ensure that height balance property is ensured. And we talked about rotations in the previous video when we introduced self-balancing BST. So AVL tree does rotations to restructure itself in insert and delete operations. Here is the insertion algorithm. We first do normal BST insert when we are inserting a node. And if inserting this node does not cause any imbalance, then we don't have to do anything. Now a question for you, when you are inserting a node in a AVL tree using BST insert, normal BST insert, then which nodes will get imbalanced? What are the nodes whose balance factor can go beyond 1? The answer is ancestors. Only the heights of the ancestors will change, and these are the nodes whose balance factor can become more than 1. So we only need to check the ancestors. So we check all the ancestors from this node. We travel up and check all the ancestors. If we do not find any ancestor whose balance factor got disturbed, when I say disturbed, it means it became more than 1, we need not to do anything. And if we find an ancestor whose balance factor became 2, we do rotations. And what rotations we do around this ancestor? That is decided by these 4 cases. It depends upon the case that you are in. Let's understand these cases with example insertions. Let's say we have these keys to insert in an AVL tree which is initially empty. So we'll first insert 20. It's a single node, so no changes in the balance factor. It's 0. Then we insert 15. 15 goes to left. Now the balance factor of 20, which is an ancestor of 15, it's 1 now, which is within the limits. It's smaller than or equal to 1. Now you insert 5. So you have 20, 15, 5. After inserting 5, you travel ancestors. So you come to this ancestor, its balance factor now becomes 1. Earlier it was 0. Then you come to this ancestor, its balance factor now becomes 2. So you have an ancestor whose balance factor is disturbed. So you need to do some restructuring. And when this ancestor and other ancestors, including the node possibly, if they form left-left case, then they are in left-left of each other. Right? So in this case, we do a right rotation. You must have guessed it also, that we need to bring the 15 at the top, 5 on the left and 20 on the right. So in left case, we do a right rotation. We bring 15 at the top. We bring 5 here and 20 here. Right? And the new balance factors are perfectly fine. You can see this, right? It's 0, 0 and it's also 0. Now let's insert more nodes. 40 we insert. So we insert 15, 5, 20 and now we insert 40. So when you insert 40, do you see any ancestor which is not balanced now? The new balance factor of this is 1. The new balance factor of this is also 1. So both are within the limits. So 40 insertion does not cause any restructuring. Now we insert 15. So when you insert 50, what happens? The balance factor of this becomes 1. Balance factor of this becomes 2. So this got disturbed, right? This is an ancestor which got disturbed. And what structure these ancestors are forming, including the node itself? They form right case. So in this case, you need to do an anti-clockwise rotation. And when you do an anti-clockwise rotation, you have the new tree as 15, 5, 20, 40 and 50. So this is your new AVL tree. Now we insert the next node, which is 18. So when you do insert the next node, 18, it's going to go where? It's going to go here as the left of 40. And you can guess what will happen, which ancestor will be disturbed. So you will travel up from here. The balance factor of this ancestor is 1, which is fine. The balance factor of this ancestor is also 1, fine. Then we come to this ancestor. The balance factor of this ancestor is 2. The difference between left height and right height is 2. It's 1 and it's 3. So difference between 3 and 1 is 2. So we need to fix this node. Now what structure is formed by the ancestors? It's right-left. So we are in the right-left case, the fourth case. And what we do in the right-left case, we do 2 rotations. We first rotate these 2. We make it right case. And then we rotate these 2 and we fix the AVL tree. I have redrawn the whole diagram with step by step. We were first in left case, then we were in right case, now we are in right-left case, and as we discussed, we'll first do a rotation around this node to make it a right case, and then we'll do a rotation around this node. And once you have practiced enough, you can do both the rotations together also, right? Because you always know when you do a rotation, your middle value is going to go at the top. So ultimately you want 20 to be at the top. But here, let's do step by step. So we'll do a rotation around 40 and what we'll get now? 15, 20, 40, 50 here, 18 will come here and 5 will come here. Right, so in the right-left case, we first do one rotation around this node and then we do a rotation around the main unbalanced node. So now we do a rotation around this. What will happen now? 20 will come here. 15 will become left of it. We are doing a rotation around this. So this will become 15 left child. Then 5 is left of 15. Right? This whole subtree is going to go to the left side. And this 20 is going to get at the root. And then 18 is going to go here. Then 40 and then 50. So this is what you do in the right-left case. You first do a clockwise rotation around these two to make it a right case. And then you do a counterclockwise rotation once you have right case to make your whole tree balanced. So we did 2 rotations in this case. And we've done an example of insertion. There is one interesting fact about AVL tree insertion. When you are traveling up and you find an unbalanced node, you do a rotation and you fix the AVL tree. The interesting thing is you only need to do one rotation. Once you have fixed an ancestor, you do not need to do anything more. Once you fix an ancestor, your AVL tree, your whole AVL tree is going to get fixed. That's not the case with delete. When you do delete a node, you follow the same algorithm. You do normal BST delete. After doing BST delete, you travel up. When traveling up, you find an unbalanced node, you see which case you are in. You are in left case, left-right case, or right-left case. You follow the rotations appropriately. And once you have done the rotations, you need to travel again to the ancestors after fixing this node. Right? That is not required in insertion. In insertion, we just need to find one unbalanced node. If there is any, if there is none, then we are done anyways. If there is any, we need to find that unbalanced node and we just need to fix that node. Whether fixing it requires one rotation or two rotation. We just need to fix one node. In deletion, once you fix a node, you might have to travel up again further to fix the ancestors. Let us now talk about time complexity of AVL tree insertion. See, your tree was anyways AVL tree before you inserted a node. So its height was theta log n. So your normal BST insert took theta log n time, and then you traveled all the ancestors. And height of your BST is theta log n. So traveling all the ancestors will require theta log n time. And these rotations that you might have to do, they are all constant operations. So overall your time complexity is theta log n only. Let us now quickly talk about height of an AVL tree. We have been saying that time complexity of insert is theta log n, time complexity of delete is theta log n because they travel across the height. Now what can be the worst case height of AVL tree? This is an example unbalanced AVL tree. It looks very much unbalanced, but it is still an AVL tree. The balance factor for this is 0. The balance factor of this is 1. The balance factor is absolute difference between left and right heights. So for this, left height is 1, right height is 2, and absolute difference is 1. The balance factor for this is 1, this is 1. So every balance factor is less than or equal to 1, so it is an AVL tree. Here is a formula for upper bound on height of an AVL tree. This is taken from Wikipedia. The formula says that the maximum height of an AVL tree can be C log 2n plus 2, where C is approximately 1.44 and plus B is also there and B is minus 1.3277 approximately. You can notice that it is pretty good as a theta log n. I mean, this constant is only 1.44. So AVL tree, even if it is slightly unbalanced, is very much considered balanced. It's very much strictly balanced if you compare it with other cell balancing BSTs like red black tree or split tree. Split tree can have in fact more than theta log n height. Red black tree has theta log n height but not as strictly balanced as AVL tree. When we talk about height of AVL tree, we'll see that the constant here is higher.